Test statistics and p-values, turning data into evidence. Step 2 in hypothesis testing is computing the test statistic. For testing a population mean when sigma is known, we use the z-statistic. Z-stat equals x bar minus mu naught divided by sigma over the square root of n. The numerator tells us how far the sample mean is from the hypothesized value. The denominator is the standard error, which standardizes this distance. In other words, z tells us how many standard errors the sample mean is away from mu naught. Let's compute z for our body weight example. With n equals 64 and sigma equals 40, the standard error is 40 over 8, which is 5. If the sample mean is 173, z equals 173 minus 170 over 5, which is 0.6. That's less than 1 standard error away, pretty close to expected. But if the sample mean is 185, z equals 185 minus 170 over 5, which is 3. That's 3 standard errors away. Very unusual if h naught were true. The p-value is the probability of observing a test statistic as extreme as or more extreme than what we actually got, assuming the null hypothesis is true. Let's visualize this on the standard normal curve. For z equals 0.6, the p-value is the area in the tail beyond 0.6. This area is 0.2743, which means there's about a 27% chance of getting a result this extreme just by chance. That's not very unusual. Now compare that with z equals 3. The shaded tail area is tiny. P equals 0.0013. Only about 1 in 800 samples would produce a result this extreme by chance alone. That's very strong evidence against h naught. For a two-sided test, the p-value accounts for extreme results in both directions. We shade both tails of the distribution. The area above z equals 3 and the area below z equals -3. The two-sided p-value is simply double the one-sided value. 2 times 0.0013 equals 0.0026. This is still very small, providing strong evidence against h naught. How do we decide whether the evidence is strong enough? The decision rule is simple. Reject h naught when the p-value is less than or equal to alpha, our chosen significance level. Here are the conventions. A p-value above 0.1 is not significant. Between 0.05 and 0.1 is marginally significant. Between 0.01 and 0.05 is significant. And below 0.01 is highly significant. For our examples, p equals 0.27 is not significant, so we retain h naught. But p equals 0.0026 is highly significant, providing strong evidence to reject the null hypothesis. Let's work through the Lake Wobegon example from the textbook. We have Wechsler IQ scores with mu naught equals 100, sigma equals 15, and a sample of 9 people with mean 112.8. The hypotheses: h naught says mu equals 100, and the one-sided alternative says mu is greater than 100. The z-statistic is 112.8 minus 100, divided by 15 over root 9, which gives us 2.56. The p-value is the probability that z is greater than or equal to 2.56, which is 0.0052. This is highly significant evidence against h naught. We reject the null hypothesis. Note that even with a two-sided test, the p-value of 0.0104 is still significant at the 0.05 level. To recap, the z-test statistic measures how far the sample mean is from the hypothesized value in units of standard errors. The p-value tells us the probability of getting a result this extreme if the null hypothesis were true. Smaller p-values mean stronger evidence against h naught, and we reject the null hypothesis whenever p is less than or equal to alpha.